Hello friends, last class I discussed about the definition of the optical fiber and the principle of the photodetector. So when we discussed principle of the photodetector, I used PN junction photodiode. It is a one type of the photodiode. Today I am going to discuss about the types of photodetector and the parameters of the photodetector. Right? So there are the three types of the photodetector. Okay. First is the PN junction photodiode, pin photodiode, and the avalanche photodiode. So based on the performance of the photodetector, these three photodiodes have been designed, right? So PN junction photodiode, that is a normal photodiode. Here you can see on the last class I discussed about the PN junction photodiode. In this PN junction photodiode, only one P and the one N-type semiconductors are there, are connected with each other. So in this PN junction photodiode, there is a depletion layer. Okay, so this depletion layer is narrow as compared to the avalanche and the PN photodiode. So when we get the narrow depletion region, we get the less response. Okay, so here we get the less efficiency and less performance. Why? Due to the, if we define the depletion region as a WD, due to the less W, we will get the less efficiency and the less performance in case of the PN junction photodiode. The working principle of the PN junction photodiode that I have discussed on the last class. Okay, now I am coming to the pin photodiode and the avalanche photodiode. What is the difference between pin photodiode and the PN photodiode? Okay, in case of the pin photodiode, the P I means intrinsic layer, N is the N-type semiconductor. That means one intrinsic layer that is sandwiched between the P-type semiconductor and the N-type semiconductor. What is the intrinsic layer? That may be lightly doped P-type semiconductor or lightly doped N-type semiconductor. Okay. So if I draw the pin photodiode, this is the P, the intrinsic layer, this is the N. So this P and N both are highly doped. Highly doped means, so in case of the P-type semiconductor, high concentration of the doping, P-type doping. Okay. In case of the N-type semiconductor, highly concentration of the N-type impurity. And the I means it may be P minus or N minus, lightly doped. The less number of majority carriers are there in case of the intrinsic layer. Okay. Now, so if we draw the PN diode, okay, so here we will get the depletion region. But in case of the PN photodiode, you will get the wider depletion region. Here you will get the narrow depletion region in case of the PN photodiode. Why normally the width of the depletion region, that is normally related with the carrier concentration. Okay, so if you lightly dope, if any material is the lightly dope, so here we will get the wider depletion region. In case of intrinsic layer, this is lightly dope, right? So here we will get the wider depletion region. Suppose this is W1, here also we will get the W1. In case of the P-type semiconductor, it is highly doped. Here you will get the less depletion region. So here you will get less depletion region. Here you will get wider depletion region. If you consider this junction, this is highly doped. Here you will get the less depletion region. Here you will get the wider depletion region. So in this way, you can tell in case of the pin photodiode, you will get the wider depletion region, because the depletion width, that is inversely proportional with the concentration gradient. Highly doped, less depletion layer; lightly doped, high depletion layer. Okay. So now In this case, in the p-n junction diode, you will get, if you draw the electric field, you will get a such kind of the electric in the depletion region. So depletion region, the electric field is very much high, but here you will get the less depletion region. If you draw the electric field in case of the p-n photodiode, so you will get a this amount of the electric field. Electric field is magnitude of the electric field is more in the entire pin photodiode. Okay, but in case of the p-n junction, only at the center of the p-n junction you will get the maximum electric field, right? Now what will happen? So whatever the electron hole pairs are produced inside the pin layer, electron hole pair. So electron hole pair will produce in the entire pin junction, pin photodiode, right? So as the electric field is maintained in the entire region, okay, as the electric field is maintained in the entire region, whatever electron hole pairs are produced inside the pin photodiode, so we will get the maximum efficiency, dissociation efficiency from this electron hole pairs, because all the electron hole pairs are dissociated. Okay, all the electron hole pairs are dissociated due to the electric field present in the entire p-n photodiode. So if all the electron hole pairs are dissociated, then you will get the maximum efficiency and maximum performance from the p-n photodiode. That is the main difference between p-n photodiode and the p-n photodiode. Okay. Now coming to the avalanche. Okay. Avalanche photodiode, the structure is almost same as the pin photodiode. Okay, so I'm not going to the structure of the pin photodiode, avalanche photodiode. I'll just discuss about the working principle of the avalanche photodiode. So what will happen in case of the avalanche photodiode? We have to apply the large reverse bias. Okay, we have to apply the large reverse bias. Okay, here I told that so two kinds of the electric fields are there. One is the internal electric field, another is the external electric field. So internal electric field, how will get the internal electric field? Okay, so if the depletion region is wider, you will get the more electric field. Okay, so how can you increase the depletion region? If we apply the reverse bias, and if the reverse bias is more, you will get the wider depletion region in the p-n junction diode. Okay, so what will happen? So suppose the p-n junction diode, we will apply the large reverse bias. Suppose more than 10 volt reverse bias you will apply. So for that you will get the wider depletion region. Okay, wider depletion region. Wider depletion region means you will get the strong electric field. Okay, strong electric field, right? Strong electric field. What is the magnitude of this electric field? That will be 3 into 10 to the power 10 to the power 3 volt per centimeter. This magnitude of electric field you will get in the p-n junction diode when you apply the high reverse bias. Okay, then what will happen? Suppose the depletion region is also wider in this case, right? So suppose electron hole pair, these are produced with application of the incident light. Okay, now so as the electric field is more strong, very much strong, so when the electron hole, after creation of the electron hole pair, this electron hole pair will be diffused, okay, transport through the junction. Okay, so but this electric field, this helps to move faster. This helps to move faster. Okay, due to this high electric field, these electron hole pair will move faster through the entire region, and this electron hole pair collide with the another atom. This electric field will collide with the another atom, and from this atom you will get a one electron. Okay, again this electron, this will move faster through the region, and this will hit the another atom, you will get another electron. So from one electron pair you will get two more electrons, right? In this way, other electron pair, this will also produce the two more electrons. Okay, in this way photomultiplication phenomena will occur. This is also known as the photomultiplication phenomena or avalanche effect. Okay, why this thing is happening? Due to the strong electric field and strong reverse bias. Electron hole pair will move faster through the entire region, and this will hit another atom. This atom, from this atom will get the one electron. In this way, more number of electrons will get. That means photomultiplication phenomena or avalanche effect. So we will get a large photo current in this case. Okay, this is the avalanche photodiode or avalanche effect. Okay, these are about the types of the photodetector and some principle of the three photodetectors. Right, now coming to the parameters of photodetector. Okay, so if you want to characterize any kind of the photodetector, we need to know some parameters, right? What are these parameters? First, I will tell about the responsivity. So you have to calculate the responsivity if you want to know the performance of the photodetector. Okay, responsivity, it is defined is the ratio between responsivity. You can define as a R. R is the denoted term, that is R is equal to JPH by I light. Okay, what is the JPH? Ratio between the produced photocurrent density by the incident optical power density. That is the definition of the responsivity. Okay, so this is the JPH is the photocurrent density, and I light is the optical power intensity. Unit of this R is the ampere per watt. Okay, so next term is the efficiency. If we will get suppose 100 ampere per watt, so this device is very much good. Okay, next is the external quantum efficiency. External quantum efficiency. EQ, this is denoted as a EQ. EQ is equal to IPH by E. Okay, here is the, what is this thing? This is the number of electron hole pair, number of free carriers are produced to generate the photocurrent divided by number of incident optical power. Okay, number of incident photon. Okay, sorry, number of incident photon. Okay, this is the number of electron hole pairs are produced and number of photons incident into the device. Okay, IPH by E, here you will get the number of electron hole pairs are produced, and P by H, from here you will get the number of photons are incident on the device. Okay, so from this relationship you will get the relationship between external quantum efficiency and the responsivity. E is equal to R into 1240 by lambda. Okay, if you know the lambda, and the lambda is the optical wavelength of the optical incident photon. Okay, so if you know the value of the responsivity, you will get the external quantum efficiency, or if you know the external quantum efficiency, you will get the value of responsivity, right? So the responsivity and the EQ, these are the EQ and the responsivity. These two are the main important parameters to determine the performance of the photodetector. Okay, so for responsivity I told if 100 ampere per watt, the device is very much good. For external quantum, if we get the 100%, that means all whatever electron hole pairs are produced, we will get the maximum free carriers from these electron hole pairs, right? But ideally you will not get, you will get the 90% efficiency. Okay. Next is the dark current. Okay. Dark current, that is the leakage current inside the photodetector when no light is there, only reverse bias is applied. Okay, that is the leakage current. Okay, due to the random generation of the carriers with applied bias, no light. Okay, under absence of the light, if you will get any free carriers, okay, with application of the reverse bias, you will get the dark current. So in case of the diode, so proper diode, you will get a less dark current in the reverse bias. But if you are getting large dark current, so diode is not. So here it is the large current, here is the less current, dark current. Okay. Next is the dynamic range. Dynamic range. It is the ratio between JPH max by JPH mean. Okay. How we will calculate this one? Log 20, log 10. This is the ratio. That is the dynamic range, means ratio between the maximum current, maximum photocurrent by maximum minimum photocurrent. Okay. And linear dynamic range, that is the formula for linear dynamic range. So if we will get the 100 dB, right, what will happen? How can you define the linear dynamic range? That is the current, we are getting the current response, right? Linear current response over a wider optical intensity. Suppose if you draw the optical intensity, suppose P of by current graph, okay, photocurrent graph. So at low intensity you are getting one response, photo response, right? At suppose 100 watt, you are getting some response. This is the wider linear dynamic, large dynamic range. This is the 100 dB. But here you are getting one response, but in case of the 100 you are not getting any response. Only the 100 microwatt you are getting any response. That is the less dynamic range. Okay. That is the linear current response over a wider optical intensity. Okay. Okay. Next is the signal to noise ratio. Signal to noise ratio. Okay. SNR. This is denoted as a SNR. So what is that? This is the ratio between maximum photocurrent by background noise level. Okay, maximum photocurrent by background noise level. Okay, I photocurrent by noise. How can you calculate the signal to noise ratio normally? So I on by I off. That means, so under illumination of light, if you are getting any current, that is the I on. Okay. So without illumination of light, if you are getting current, that is the noise current. That I told, dark current. Okay. Without illumination of any light, if you are getting any current, okay, if any random generation of carriers are there, you will get current under reverse bias. Okay. This will be the I, this will be the I off. So if you get this ratio, you will get the value of signal to noise ratio. Okay. Okay, so for I off, that should be minimum. Okay, this should be in the nano ampere range, and your I on will be the milliampere range, so that you will get the high signal to noise ratio, less dark current, less noise, and the high power, high photocurrent. Okay. Next is the specific detectivity. Specific detectivity. D star. This is denoted as a D star. So this is used to determine the performance of the noise in the photodetector. Okay, if any, so if you have the high detectivity, that means the device has the less noise. Okay, but if you are getting the less detectivity, the device have the less noise as well as the less photo response. Okay, so this is defined to determine the noise performance of the photodetector. Okay, now how many types of noise are there? There are the three types of noise: short noise, thermal noise, and the flicker noise. This flicker noise from thermal fluctuation. Okay, now coming to the short noise. What is the short noise? When we will get the short noise? Okay, this is the random fluctuation in generation and recombination process with bias condition. Okay, so if any fluctuation is there in generation and recombination process with the application of the bias, you will get the short noise. How can you so if short noise is there, so how can you calculate the specific detectivity with the presence of short noise? So that is the specific detectivity is equal to R by root under 2 J dark Q. Okay, this is the formula for calculating the specific detectivity if the device has short noise. Okay, right? So the J dark is the dark current with application of the bias. Okay. Next, coming to the thermal noise. Okay, thermal noise is the thermally generation of the electron hole pairs without application of the any bias. Okay, thermally generation. If you will not apply any reverse bias, that time also you will get some photo response. But when you are not applying any bias, still you are getting any carriers. So this is the thermal noise. Okay, so that means thermally generation of carriers without bias. Okay, what is the formula for calculating detectivity? D is equal to R into A RD by 4 kb T. Okay, so what is the R? R is the responsivity. This R is the responsivity. A is the active area of the photodetector. RD is the zero bias differential resistance, and 4 is the 4 kbd. Kb is the Boltzmann constant, and the T is the temperature. Okay, so two ways you can calculate. If you are applying any bias, that means the short noise is the dominating factor. Okay, if you are not applying any bias, then thermal noise is the dominating factor to calculate the specific detectability or noise performance. Last term is the response time. Last term is the response time. Okay, what is this? It determines the speed of the response of photodetector. Okay, and that is how fast a detector can sense the optical signal. Okay, this is determined by the response time. Okay, response time, it corresponds to time taken to produce free carriers from the bounded electron hole pairs. Okay, this is the definition of the response time. Time taken to produce the free carriers from the bounded electron hole pairs. Right? The response time, that is related to the two terms. One is the rise time, another is the fall time. Okay, so how can you calculate the rise time? Rise time is the rise time. Okay, that is time required for transition for transition 10% to 90% of peak photocurrent. Okay, time required for transition from 10% photocurrent to the 90% photocurrent. So here, so if you want to get the photocurrent, if light is off, you will get the zero photocurrent almost, right? So when light is on, you will get the photocurrent like this way. Ideally, you should get the this graph. Okay, this is the off condition, this is the on condition. Okay, so how fast the transition is taken from the on condition to off condition, that determines the response time. Okay, so here if this is the magnitude, maximum magnitude, this will be the 10% photocurrent, this is the 90% photocurrent. Okay, this time is the rise time. Okay, fall time is the opposite way. Time required for transition from 90% to 10%, it determines the fall time. Okay, so if this time is very less, that is the fast response. If the TR or F is the more, then you will get the response, less response. Means the device requires so many times to generate the photocurrent. Okay, for case of the less response speed. So if the less time, that means fast photo response, right? So when we will tell that the photodetector is the faster photodetector, if you rise time or fall time is in nanosecond, 10 nanosecond or 20 in the order of the nanosecond, that means the device is the faster device. Okay, so these all are about the parameters of the photodetector. Next class I will discuss about the application of photodetector and the another parameter, that is the phototransistor. Thank you.